So I'm going to run through how to do this truss analysis problem. Your numbers will probably be different than mine, but the steps are still the same. So the first thing we need to do this problem is find the force of water that's acting on the truss. So we have the volume of water, which is 6 cubic meters, and we want to convert that to a force. We can use a couple relationships to do so pretty easily. So starting out, we know that 1 milliliter of water is equal to 1 gram of water. Using that, we know that 1 liter, which is 1,000 milliliters, is equal to 1 kilogram of water, which is 1,000 grams. 1 cubic meter of water is equal to 1,000 liters of water, which is equal to 1,000 kilograms of water. So we have 6 cubic meters, which is equal to 6,000 liters of water, which is equal to 6,000 kilograms of water. But we're asked to find the force in newtons and not kilograms, so we need to convert from kilograms to newtons, which we can do so pretty easily. So to convert from kilograms to newtons, we're going to use the gravitational constant on Earth, which is 9.807 meters per second squared. So to find force, which I'm going to call just F, we'll take the weight of the water, which is 6,000 kilograms, and multiply that by the gravitational constant, which is 9.807 meters per second squared, which gives us roughly 58,842 newtons. So the answer to the force of water acting on the system, in my case, is 58,842 newtons. For the next question, it just is asking how much of that force is acting on each of the columns. So we're making the assumption that the truss has 4 columns and the force is evenly distributed between those 4 columns. So you just divide 58,842 by 4 and you get 14,710 newtons. Again, this is the answer for my case. Your numbers will be different most likely, but the steps to get the answers will be the same. So now that I have the forces acting on the truss by the water and the wind load known, I can move into breaking the truss into its individual joints to do the analysis at each joint. So again, the first thing to do when you're doing a truss analysis is to break the truss apart into its individual joints so you can do an analysis at each joint rather than trying to analyze the whole truss in one go, because if you do that, if you try and analyze the truss in one go, it's going to be extremely difficult. So what you want to do is break the truss into its individual joints A, B, C, and D, draw the forces acting on each joint, and then analyze each joint by itself. So I'll go ahead and draw the 4 joints to the right, and I'll draw the forces that are acting on each joint. So first we have joint B, then joint A, then joint C, and joint D. The first forces that I'll go ahead and draw are the forces acting on the truss by the water and the wind. So at joint B, we have force F1 from the water. At joint C, we also have force F1 from the water, from where we assumed that the 4 columns within the truss will have the same load from the water. Also at joint C, we have the wind load, F sub 2. And for now, I'm just going to leave the forces F1, F2 as their names and not the actual values. When we get into analyzing each joint, I'll start writing the values of the forces. But for now, just to keep it clean, I'm going to keep just the names, the lettering of the forces. At the bottom of the truss, we have the supports. At joint A, we have a pinned support. A pinned support resists movement in the x and the y direction. So I'll go ahead and draw a force in the x direction, which I'll call A sub x, and a force in the y direction, which I will call A sub y. At joint D, there's a roller support, which only resists movement in the y direction. So I will draw a force in the y direction and call it D sub y. Now, these forces are not the only forces acting on these joints. There's the forces within each of the members that are acting on the joints as well. And I'll go ahead and draw the forces from each member at the joints as well. So I'll start with member AB and draw those forces. So at joint A, there's a force from member AB, which I will call F sub AB. And then since these are equal and opposite forces, this same force has to be mirrored at joint B. So again, that is F sub AB. I'll move to member BC. So at joint B, there's a force F sub BC. And since they're equal and opposite, it needs to be an F sub BC at joint C. And actually, I know that's going to be in the way of one of my other forces. So let me move that right to there. Now I'll move to member CD. At joint C, there'll be a force going into that member. I'll call that F sub CD. At joint D, equal and opposite, F sub CD. Member AB, member AD, the bottom member of a force going from joint A, F sub AD, and then equal and opposite at joint D, F sub AD. The final member is the cross member, AC, so going from joint A, F sub AC, and then equal and opposite at joint C, F sub AC. Now, this is each joint broken apart with the forces acting on it. So moving forward, I will go through joint by joint and solve the forces acting at each joint. So then we'll end with a truss where we know all the forces acting at each point. So now that we have the truss broken up into its individual joints and all the forces at each joint drawn, the next step is to determine what joint to start the analysis at. So when you're doing a truss analysis problem, you want to find a joint where the number of known forces equal the number of unknown forces. So in our case, we're going to start at joint B because we know force F1 is 14,700 newtons. We don't know force F sub AB, but since it's in the vertical direction, it's going to equal F1. And then we also don't know F sub BC, but since there is no X force at joint B, F sub BC is going to be equal to 0. So again, we're going to start at joint B because F1 will equal F sub AB, and then F sub BC will equal 0 due to there being no X force on this joint. So now that we have chosen joint B as the joint to start with, we can go ahead and find out what force F sub AB equals and what force F sub BC equals. First, let me remind you about the assumptions we make in terms of the direction of the forces. We assume that forces pointing up are positive and forces pointing to the right are positive. So that means that if a force is pointing down or to the left, we assume it's negative. Also, to solve a joint, we need to make sure that we're satisfying the sum of forces in the y equaling 0, as well as the sum of forces in the x equaling 0. So we will start out with the sum of forces in the y, which equals negative 14,710 newtons, because the force is pointing down, minus F sub AB, because I drew that arrow pointing down. This means, from this equation, F sub AB equals negative 14,710 newtons. So what this negative value here means on this force is that I simply drew the arrow the wrong way in my free body diagram when I was breaking the joints apart. So this arrow right here should actually be pointing up, because the force in the F sub AB needs to cancel out the force of the 14,000 newtons. So again, the negative that I have here on the F sub AB just means that I drew my arrow in the wrong direction, and it should actually be pointing up, which I will show when I draw the joint here in a second after I do the sum of forces in the X. So moving to the sum of the forces in the X direction, we only have one force in the X direction, which is F sub BC, which means that F sub BC is equal to 0. Messed that up. Let me erase that and draw it correctly. So again, F sub BC is equal to 0. And now I'll draw joint B with the known forces now, and you'll see what I was talking about with how I drew my F sub AB force arrow in the wrong direction. So we have the force from the water, which is 14,710 newtons. We have the force in F sub AB, which, to cancel out the force from the water, needs to be pointing in the opposite direction. So it needs to be pointing up. And then we have 0 newtons in F sub BC. So that is how we solve the forces at joint B, and now we'll move on to the next joint. So now that we have joint B analyzed and know all the forces acting on joint B, we can now move on to the next joint. The question is, what joint do we move on to? We can look at joint A, but there's a force in the y direction for F sub AB, A sub y, and the y component of the F sub AC force. So there's 3 unknown y's, and we would only have 1 known y from the B joint. So that's not the right answer. We can look at joint C. We know force F1, we know force F2, we know force F sub BC, but we don't know the x or the y component of the F sub AC force, and we don't know the force F sub CD. However, we can figure out the x component of the F sub AC force and then use trigonometry to figure out the F sub y, or the y component of the F sub AC force, so we can figure out all the forces in joint C. So joint C is the next joint we'll move to. So since I said that we would be using trigonometry to calculate a few of the angles at joint C, that means that we need to know the angles within the truss, specifically the angles for cross member AC. To do this, we can use SOHCAHTOA, where the sine of the angle equals the opposite over the hypotenuse, the cosine of the angle equals the adjacent over the hypotenuse, and the tangent of the angle equals the opposite over the adjacent. In our case, we know the opposite and the adjacent, so we can use tangent, where opposite is 75 meters and the adjacent is 37.5 meters if we're solving angle 1, which is what we're going to do first, and then we can get angle 2. So to solve for angle 1, for this angle first, we'll use tangent, so it'll be tangent of angle 1 equals 75 over 37.5. Angle 1 equals the tangent inverse of 75 divided by 37.5, which equals 63.44 degrees. To get angle 2, we can just subtract angle 1 from 90, since we know this angle is 90 degrees and we know a triangle has to add up to 180, so that means that these two angles have to add up to 90, so that this whole triangle adds up to 180. So we can subtract angle 1 from 90, which gives us 26.56 degrees for angle 2. And we'll be using angle 2 and angle 1 for calculations at joint C and joint A later on. So now that we know the angles for cross member AC, we can move to calculating the forces acting on joint C. First, we need to break F sub AC, this force right here, into its component forces so we can use them for summing in the Y and X directions. So we will break F sub AC into its component Y force, which I'll call F sub AC sub Y, and its component X force, which I'll call F sub AC sub X. It's also important to note that the angle for F sub AC will be the same as angle 2 for the member AC, which will come into play here in a little bit. I'm going to draw a box around this just to keep it away from everything I'm about to do. So we can move to summing forces in the X and the Y. We'll start in the X. So sum forces of the X equals 0 equals 250 newtons minus 0 newtons minus F sub AC sub X. From this equation, from summing in the X direction, we can see that F sub AC sub X is equal to 250 newtons. Moving to summing in the Y direction, we'll do sum of forces in the Y equals 0 equals negative 14710 newtons minus F sub CD minus the component force of F sub AC in the Y direction. So the issue here is we have two unknown forces, and which means we can't solve for both forces because we don't have a means to. But we can use F sub AC and some trigonometry to solve for F sub ACY, which will then let us solve for F sub CD. So going back to my breakout of F sub AC, we can use SOHCAHTOA again, like we did on the last slide, to find the angles. We can use SOHCAHTOA to find the missing force. So looking at angle 2 and F sub AC and X and F sub AC of Y, we can use tangent, where we know the angle, we know the opposite force and the adjacent force. So using tangent, we'll use tangent of 26.56 0.56 degrees, angle 2, which is the same for the cross member, and force F sub AC equals the opposite force, which is F sub ACX, divided by the adjacent force, which is F sub ACY. This makes it so F sub ACY is equal to 250 newtons over the tangent of 26.56 degrees. And the tangent of 26.56 degrees is just 0.5, which makes it so F sub ACY is equal to 500 newtons. To find the overall force of F sub AC, which we'll need when we go to joint A, we can use Pythagorean theorem. So F sub AC will just equal the square root of F sub ACX squared plus F sub ACY squared, which is just C equals the square root of A squared plus B squared. It's how you find the hypotenuse in a triangle. And this makes it so F sub AC is equal to roughly 560 newtons. Finally, going back to our summing of forces in the Y to get our F sub CD, we now know our component force F sub ACY. So sum of forces in the Y equals 0 equals negative 14710 newtons minus F sub CD minus 500 newtons. This makes it so F sub CD, or negative F sub CD, is equal to 14,710 newtons plus 500 newtons, which is equal to 15,210 newtons. And moving the negative sign, FCD equals negative 15,210 newtons. And all this negative sign right here means is that I drew my arrow for the force F sub CD the wrong way, and the force should actually be pointing towards joint C, so that force should actually be pushing onto joint C and not pulling away from it. So now that we know the forces at joint B and joint C, we can move to joint D, which is going to be the next easiest joint to do. We know the force F sub CD is equal to 15,210 newtons, which will give us the D sub Y force, and we also can find the force F sub AD. Since there are no other forces acting in the X direction, that means F sub AD is going to be equal to 0. So moving into joint D, very quickly looking at joint C, this force, the 15,210 Newton force, is the force F sub CD. Now, since forces have to be equal and opposite, the force that I have listed, or the arrow that I have drawn for F sub CD at joint D, cannot be going in the same direction as the arrow that I have drawn at joint C. So based on my analysis at joint C, I know that the force F sub CD is pushing towards joint C, which means that the force at joint D, being equal and opposite, needs to be pushing towards joint D. So the F sub CD arrow at joint D should be pushing down onto it rather than pulling away from it. And again, that was just an assumption I made when I was drawing my free body diagrams for the joints, and it's an easy fix. So in our case, at joint D, F sub CD is pushing down, so it is a negative force. So it equals negative 15,210 newtons at joint D because it's pushing down onto joint D. So moving into summing forces, sum of forces in the Y is equal to 0, which equals negative 15,210 newtons, which is the force F sub CD, and then plus D sub Y. This makes it so D sub Y is equal to 15,210 newtons. And then moving into summing forces in the X. Sum of forces in the X equals 0, which equals the only force going in the X direction, which is F sub AD. This makes it so F sub AD is equal to 0 newtons. So now that we know the forces at joint B, joint C, and joint D, we can move to solving the final joint, which is joint A. So moving into joint A, luckily most of the forces at joint A have already been calculated elsewhere, like F sub AD was calculated at joint D, F sub AC was calculated at joint C, and then F sub AB was calculated at joint B. It's also worth noting that I flipped the direction of my arrow for F sub AB at joint A. Elsewhere in the video, I had that arrow pointing away from joint A, which was just my assumption, but after going through the analysis at joint B, I realized that that arrow needed to be pointing towards joint A to be equal and opposite of the force at joint B. So F sub AB is equal to negative 14,710 newtons, and it's negative because it's pointing down, it's pointing towards joint A. F sub AD is equal to 0 newtons, and then F sub AC is equal to 560 newtons. And I'll go ahead and break F sub AC into its component forces for use in summing in the X and Y direction. So that is F sub AC. F sub AC sub X is equal to 250 newtons. And then F sub AC sub Y is equal to 500 newtons. And if you need to see how I calculated those component forces, I did that at joint C. So moving into summing forces in the Y direction, sum of forces in the Y is equal to 0, which is equal to negative 14,710 newtons from force F sub AB plus A sub Y, which is the Y force from the pinned support, and plus 500 newtons, which is the Y component of F sub AC. Solving this, it gives you A sub Y is equal to 14,210 newtons. Moving into summing forces in the X, sum of forces in the X equals 0, equals A sub X which is the X force from the pinned support, plus 250 newtons, which is the X component of F sub AC, plus 0 newtons, which is force F sub AD. Solving this, it gives you that A sub X is equal to negative 250 newtons. And this negative sign, again, just means that I drew my arrow for A sub X at joint A in the wrong direction, and the arrow should be pointing away from the joint. So to wrap up this truss analysis, here is the final breakdown of the joints with all of the analyzed forces that are acting on each joint as well as the forces that are acting on the truss.